I'm getting pretty good at this. Oh, okay. Maybe not as good as I thought. And we're gone. And we're gone. Alright, so to get started, I have just imported one of the ships into the scene, and this is the pack I'm using. It's completely free, has a bunch of low poly ships, so this will allow us to do ship customization later on, and maybe also have different enemy types and stuff like that. I've just imported that in, also made a ground, which is just a plane, and gave it kind of like a Mars looking color. My player object is actually an empty, and my model is a child to that. And so on my player object, I'm going to make first a rigid body, because we will be making rigid body based movement. I'll have a drag of 0.5 on there for now. I will say interpolate and collision detection. For now we'll say discrete, later on we might change it to continuous, and all this is fine. I'm going to start off by implementing the hovering, and so essentially I'm going to do a raycast down, which is going to have a maximum distance of hover distance, and if that raycast does not detect anything, it will apply a gravitational force downward. So the spacecraft will move down. If the raycast does detect something, it'll apply a hover force upward, and that will just, keep the spaceship from actually hitting the ground, ideally. And after it goes up a certain distance, the raycast will no longer be long enough to detect the ground, and so, it'll fall back down, and so it'll stay around this equilibrium, which will be hover distance. And so let's implement that real quick. So I'm going to create a C# script. We're going to call it player vehicle movement. Alright, attach it onto player and open it up in Visual Studio. First thing we will need is a public float hover distance. We'll set that in the inspector every frame. Should we do every frame or should we do fixed update? Let's do fixed update. And so fixed update gets called, it's every 0.02 seconds. But actually I might change that to 0.01. So let's go over here, project settings. Where is it? Time, and here fixed time step. Right now it's 0.02 seconds, and so let's change that to 0.01. Alright, so that's perfect. And so in fixed update we'll actually do our physics and raycasting. In here we need a ray, so let's create a ray. So an array needs an origin and a direction, so we'll just say our transform.position, and the direction is just going to be vector3.down. And I am using vector3.down and not transform.down because I want it to be the global down vector. So we can raycast our downward ray. Downward ray. Maximum distance is going to be our hover distance. And right now I don't need to put a layer mask on there. Later on maybe I'll put a specific ground layer mask on there, but that should be good. Let's put this inside an if statement. We also need a out variable that goes before the max distance, and so we'll do out new raycast hit. Do I have to put new here? Out, raycast, hit. Okay, yeah, so no new needed. I'm a bit rusty. It's been a little bit of time since I did Unity programming in C#. Okay, so here we apply hover force, and we'll do that in a second. Otherwise, we will apply gravitational force. To do that, we will need our rigid body, and we can get a reference to it right here. Get component rigid body, and we know that we're going to have a rigid body attached, so we shouldn't have to do any checking there. And so if we apply hover force, we are going to need that. So hover distance, and we'll also do hover force, and we'll do gravitational force. It's going to take in the vector of the force. That's going to be our hover force times vector3 dot up, and again I'm doing vector3 dot up, not transform dot up, because I actually do want the global up vector. And that should be good. We don't need time.delta time because we're doing this inside fixed update, so it's not based on the frame rate at all. And otherwise, apply gravitational force. We'll do rb dot add force, and this will be our gravitational force times vector3 dot down. And that should be good. That should be our hover. Let's actually make a hover function, and we'll put this in there. Inside this function, I also want to add some debugging, just so I can visualize what's happening. So I'm going to do debug.drawLine from transform.position to hit.point, because in this case, you know, if this if statement evaluates it true, that means hit.point is not null. Or hit isn't null, and I can access the point. And we'll say, since it's hitting something, we'll say color.green, because that's what we did in the drawing. I realize now, perhaps this is a bit confusing if it's green when it hits something. I don't know. But yeah, we'll make it green when it hits something, and if not, if it doesn't detect anything, it'll just do, it'll make it red, and hit.point will not exist, so we'll have to do transform.position plus downward ray dot direction, and we'll multiply it by hover distance. So we start at our position and we add the displacement, which is right here, and so that will give us our final point that we end up at for the second point, and we will make it red. Let's come over here, hover distance, let's set it to 8. How about that? Hover force, I have no clue what that's gonna need. 100 hover force, 50 gravitational force. I don't know if that's going to be correct at all, but let's see what happens. Oh, not good. Where'd it go? Why are you down here? Alright, well, obviously it's not detecting stuff. What could be going wrong? Oh, non-convex mesh collider with non-kinematic rigid body is no longer supported. Ah, I see. So because this object has a rigid body and its child has a mesh collider, its child's mesh collider must be convex. You just click it right here, and let's try this again. Here we go. Look at this! We are hovering at hover distance. And so let's move hover distance up. So let's move it to like 12. As you can see, it moves up. Now, the first thing you'll notice is that our ship is no longer staying upright. So the next thing we will implement is the ability to correct itself and maintain upward, posture. Because right now, as you can see, it is hovering. It's just not righting itself in any way. But yeah, that's awesome. Also, I do plan on eventually making hover distance based on a sine wave, so we can actually tell it the frequency, the minimum hover distance, and the the amplitude of the hover. So it'll actually go up and down a little, which will look better when it's being done by a sine function with a low frequency, like something like this. Alright, so here's our ship. A is the global up, and B is the ship's local up vector, because the ship is going to have some rotation that isn't perfectly upright. We could just do a quaternion.lerp, but that won't interact with the physics or the colliders in the environment. And so we want to instead apply a torque on the ship, so something that we'll call it T. I was going to use M for a moment, but since we're talking about torque, we'll call it T. And this torque's axis is actually going to come out, and right now it coincidentally happens to look as if it will always go with the forward vector of the ship, but B can be in any plane. So this vector, we'll call this C. This is the axis of the rotation about which this torque is applied. C is actually going to be dependent on A crossed with B. So it's going to abide by the right-hand rule. C will be orthogonal to both A and B. And if you're not sure how cross products of vectors work, let me know. Maybe I can make a video about it. But yeah, so that's how we'll find C. We'll take the cross of A and B, and then we'll apply a torque about that. So our torque is actually going to be, our torque vector is going to be some correction speed, we'll call it K, times C. Alright, so here in the code, I've created a new function called self-correct rotation, and here's its definition. So we'll get started by first creating a float angle, which will be the angle between our global up, which is vector3.up, and our local up, which is transform.up. And we'll say if our angle is greater than 5 degrees, because this does return it in degrees, I believe. Yes, returns the angle in degrees. So if it's greater than 5 degrees, that's when we need to apply our torque. So firstly, we'll have a vector3 called the axis, which will be in our diagram, it'll be C. And that will be the cross, vector3.cross, of our global up, which is vector3.up, and our local up, which is transform.up. Then we'll get our torque, which is another vector3, if I can type, and that will be a constant times our axis. The reason we want a constant is because we want to be able to control how strongly and how quickly the correction torque, is applied to the vehicle. So if we come up here, we'll create another public float, and I'll just create a new section here. Public float, self-correct speed. And so we'll just do self-correct speed times that axis. So I just added some debug draw line commands. So this one will draw the global up vector as a blue line. This one will draw the local up vector as a cyan line. And if a torque is applied, this one will draw the axis of rotation with a yellow line. So yeah, let's see if everything's working. Let's rotate it a bit. Okay, well, that's not good. What is the issue here? Perhaps the speed is too slow? No. Too fast? Oh, are we seeing some movement? Alright. I'm stupid. I might be the stupidest person on the planet. So we calculate this torque, never do anything with it. All right, let's do rb.add_torque. Crazy. Let's add this torque. Oh, I'm a lunatic. I'm an absolute crazy person. Okay. Let's apply a rotation here. Let's actually pause it and apply a rotation. And so here, let's go one frame forward. So now you can see that our local up vector is right here. The global is right here. And so we want these two to match up. We take the cross product of them, which is this. And you can see it's perpendicular to, if these two lines were in a plane, this vector is normal to that plane. All right, okay. We'll need a higher value here. So let's do 10. Anything? Okay, still nothing. Let's do 50. Let's also make it hover at a higher altitude. All right. So it seems to be wanting to make it upside down. All right. What are we not considering here? Something's backwards. I have a feeling that if we just negate this, that will fix our problem. So after reviewing my drawing, I figured out why the negative sign is required. So if you look here, according to the right hand rule, if you point the thumb on your right hand in the direction of a vector, which in this case is the axis of rotation of the torque, then it will tell you the direction of that rotation. So in this case, you can see when the thumb is pointed in this upright direction, you can see the fingers curl counterclockwise, not clockwise. And here in my drawing, I had drawn this torque clockwise. So in reality, this torque would not be going clockwise. If C is our vector that we're using, then the torque would go counterclockwise like this. And so it would push B away from A, or rotate B away from A, and it would keep rotating until it's at its furthest point away from A, or furthest rotation away from A, which, is just the opposite rotation from the global up vector, which is the global down vector, which is why our ship constantly ended up flipping upside down. That's why when we applied this negative sign, you can either think of it as flipping this vector and continuing to use the right hand rule to find torque, or you can just think of it as flipping the right hand rule so that it goes in the opposite direction. So technically, I guess you could say it's the left hand rule at that point. So now if you point your left hand in the direction of C, or your left thumb in the direction of C, you can see your fingers will curl clockwise, which will give us this original torque that we had wanted. Let's make the hover height 15 by default. Let's make this like 50 by default. Alright, let's pause it. Let's apply a rotation to it. Something like that. There we go. And play. Ooh. There we go. That's what we want. Maybe a value larger than 50, and maybe less than 5 degrees. So let's come up here. And where is it? Instead of 5 degrees, let's say 1 degree. So you get 1 degree to move around. Let's also start it at an awkward angle, just to begin with. Alright, that seems to be about what we want. Definitely want this to be stronger. Let's try 150. Perhaps the problem is actually, maybe 100 is enough. Perhaps the problem is the angular drag. Let's turn that up to 0.5. And let's turn normal drag up to 1 as well. There we go. That's about what we want right there. And so if I perturb it, it'll go right back to its position. And now we can turn this up to like 175 maybe to get a faster response time. This is about what we want. Very nice. All right. Perfect. And if we move it up, it'll come down until it hits its equilibrium. Bring them all the way up and drop them. There we go. Very nice. So I did some of the setup for player input on my own. I just imported the input system, the new input system, and I created a player input object and told it to generate a player input C# class so that I can use it in my code. And in the player input object, I created a vehicle action map. And in the action map, I just created a move action, which is handled by WASD through this composite. And a controller can also cause movement, but it's also using a composite because my left and right trigger are actually my acceleration and deceleration. And so I couldn't just use the left stick because, I wanted the left and right trigger to be in there. Another thing is, whereas WASD has this digital normalized mode, the controller is actually analog mode, and I have these dead zones here because my controller has a little bit of stick drift. And I'll show you the effect of that in just a second. So here in the code, I reference the player input, the C# class that it generated. In awake, I set it to a new instance of that player input, and the reason I call this in awake rather than start is because awake gets called before this enable function. So if I set this new instance in start, this enable function would be called before it gets actually set to an instance, and that causes an error here, a null reference error, because it's trying to enable something that doesn't exist yet. And so I had to put it in awake, and then In update, and the reason I'm doing it in update and not fixed update is because I want this, I want player input to be taken into account every single frame so it feels smooth and responsive. In update, I just pass in the vector2 value of move into this movement function that I created. And currently the movement function isn't actually moving the vehicle at all, it's just printing out dir colon and then the direction vector. And so we can actually see that it's working here. So let's run it. And first I'll use WASD. You can see by default it's at 0, 0, so no movement would occur. If I press W, you can see the Y value is 1, which means I'd be moving forward. Same thing with S. Now it's -1, so I'm backwards, moving left, moving right. And, I can do any combination of these. As you can see here, since I'm pressing W and D at the same time, it normalizes the input and I get 0.71 in each direction. So my overall speed, the magnitude of my speed, stays the same. Now let me take out my controller and let's do accelerate. So RT, I'm going to press it down halfway. So about this much. Oh, okay, so it wasn't a perfect halfway. So you can see how I can actually get fractional values, or, decimal values, as opposed to, just a hard 1, depending on how much I push down the right trigger. And left trigger, you can see now it becomes negative, and then turning left, turning right, there you go. So now we need to use this vector2 to move our vehicle. So first thing we can do is we'll need some speeds. So let's do speed and turn speed. So for moving forward and backwards, we'll say if direction.y, that's our forward backwards axis, is greater than, or let's say is not equal to 0, so it could be positive or negative, but it's not equal to 0, then rb.add force direction.y times speed times transform.forward times time.delta time. The reason now I have to do time.delta time, also let me move this over here actually, because it's good to put your vector at the very end and all your constants in front of it according to Unity's syntax. The reason I have to multiply by time.delta time now is because this movement is being called an update, so it is frame rate dependent, and so time.delta time just allows me to make it frame rate independent. So that should be my forward and backwards movement done, and we'll worry about the rotation in a second. Let's just see if we can start moving our vehicle. Oh yeah, I should have mentioned, I also parented the camera to the vehicle, just as a preliminary thing. I'll eventually create a camera script to create smooth camera tracking, as opposed to the rigid tracking that we have now. But if we press W, oh wait, one thing we didn't do, we had to set the player's speed. So let's set it to, like, I don't know, 100? That sounds about right. And W. And W. Okay, let's set it to like 2500. 2500. I'm a lunatic. Alright, let's see what happens now. 2500 should be about right? If 1000 was moving like that. Okay, so definitely still could be faster, but not bad. And then press going backwards. There we go. Very nice. Let's turn this up even more, though. Double the speed once again. There we go. Okay, so next we have to implement actual turning. So we'll say if direction.x does not equal 0, then rb.add torque, And the torque will be our direction.x times our turn speed times time.delta_time times transform.up, so our local up vector. So we will rotate about the ship's local up vector. Turning left very slowly. Let's turn this up to 1,000. Oh, look at us turning left. Hey, okay, so let's turn this up to 10,000. There we go. Now we're getting the response time we want. Angular drag perhaps could be increased a little. 0.8 perhaps. Turn left. We let go. It spins for a little bit but comes to a stop. Move forward. Let go. Moves forward a little bit and then comes to a stop. Very nice. Very nice. Now, one thing you'll notice is this turning feels extremely rigid. It's because ideally, we would want this ship to turn about its longitudinal axis, the axis that goes right through it. Its local z-axis comes straight through. And so we want to rotate about its local z-axis, its local forward axis, whenever we turn, because that will give the turn a little bit more oomph to it. So not only will we add a torque about its local vertical axis, we also want to do rb.add torque, and this will be, we'll call this the turn modifier. I don't know if that's the best name for it, but we'll call it that. So we'll do direction.x times turn modifier times time.delta_time times transform.forward. So it's applying this rotation about its forward axis, like we said. So let's see if this does at all what we want it to do. So we'll turn modifier to like 2500. Let's see what happens. This might not do what I want it to do at all. So let's come to a standstill. Turning left. Okay, so it's turning the opposite direction as what I want. So right now it's turning away from the turn. I want it to turn into the turn, right? So we will just negate this for reasons mentioned before. It'll just flip the rotation. So we turn right into the turn, as you can see. Turn left, we turn left into the turn. We bank left is what I'm trying to say, I guess. So yeah, there we go. Now if we move forward, we actually have a somewhat robust moving system. Definitely need tweaking, like the turning is way too slow right now. The camera being so rigid definitely sucks a lot of life out of the movement. But as you can see, it is more or less working. And then that happens. There we go, we righted ourselves. Alright, so I've made some changes. First of all, in movement, instead of just one speed value, I now have an acceleration and a deceleration, which gets used based on whether we're moving forward or backwards. I also have this look controls function, which calculates a displacement based on theta, phi, and the radius, which are spherical coordinates up here. And so how spherical coordinates work is instead of using XYZ, they use R, theta, and phi to denote a point in 3D space. It still takes three numbers, just like XYZ, but it's easier to be thinking about, oh, if the camera is rotating, theta is going from 90 degrees to 180 degrees. So it's just easier to think about it in spherical coordinates. And so Unity still uses Cartesian coordinates, XYZ, so we have to convert it back. And so here, in our displacement, which I tried displacement a couple different ways. First I had global displacement, but that felt really awkward because if you turn the vehicle, the camera wouldn't turn with it. So that was very awkward. I then had a local displacement with a global up vector. That also felt very rigid and just wasn't behaving the way I wanted it to. Whereas this one felt like it wasn't tracking the vehicle well enough. The local displacement was just, it felt far too rigid. And so I came up with kind of like this hybrid, which you can see the equations I have written down here, but it I think it strikes a very nice medium between the two. And so let's check out what all that means. So as you can see, I can rotate my mouse around and look around, and I can press R to reset the camera. So if I'm over here, I can press R and I'll reset to the original position, and we can start moving. And as you can see, the camera will actually smoothly follow the ship, and it will actually even get closer and further based on the speed of the ship, which I think is a very nice effect. And that's just a byproduct of the fact that we're using a lerp function to go from the camera's current position to its intended position, as opposed to just setting the camera's position instantly to that intended position. To make the movement feel a lot better, I wanted to implement this jump and boost function. I also want to implement an aileron roll kind of function, but maybe that will come in a later video. So in the same way that we have reset camera here, which is just connected as a delegate to this controls action for a reset camera, jump is a delegate of the jump action, and boost is a delegate of the boost action. And actually, I can show you that right here. So in our player input object, just like we have move, just like we have look, we have reset camera, we also have jump and boost. And so the three functions you saw earlier are delegates of these three. And so we can come down here, and for jump, we're just going to want to apply a vertical force that we want to specify. So let's come back up here actually, and let's say public float jump force. And we'll also say jump cooldown time. We'll also ask for, while we're here, boost force and boost cooldown time. We also want some local booleans. So bool can jump and can boost. And that way we can check if we actually can jump. So we'll say if can jump, then rb.add force in the vector3.up direction, and it will be jump force times that. Right underneath the jump function, it doesn't have to be right underneath, but just for simplicity's sake, I'm just going to put it right underneath. I'm going to have a coroutine called jump cooldown, and that coroutine is going to set can jump to false. It's going to yield return new wait for seconds jump cooldown. Nope. I just called the function in itself jump cooldown time. There we go. So it's going to wait for however many seconds we specify jump cooldown time is, and then it's going to set can jump back to true. And right up here, we're just going to start this coroutine. Jump cooldown. There we go. So every time we jump, we're first going to check if we can jump. If we can, we'll jump, we'll add the force necessary, and then we'll start the cooldown. So the cooldown will set can jump to false, meaning while this time is elapsing, you cannot jump anymore. After this much time has elapsed, can jump will be set back to true, and you'll be able to jump again and repeat the process. We're going to do the exact same thing for boost pretty much, but instead of add force vector3.up, it'll be add force transform.forward. That should be our boost and our jump taken care of. Alright, Now with the jump and the boost implemented, movement is already starting to feel much more maneuverable and satisfying, unless you crash into an obstacle just like that and take a tumble. But I made the ship turn much quicker, and that just, it makes it feel more nimble and just reduces some of the frustration with the slow turning. I think honestly this turning rate makes it very satisfying. It's not too quick, but it's not as slow and sluggish as it was before, and the tumbles, I think, are very satisfying. There are 2 points that I'm kind of having some struggle on. Chill out, camera. So the camera is still not perfect yet, but the first thing I want to touch on is actually to do with the camera is when we're moving fast, because I'm lerping to the intended position. So here, let me get on a straightaway here. So because I'm lerping to the intended position, if I try to move the camera to the front, it won't actually get to the front because it can't catch up to that point. And so I'm not really sure what to do about that. I could maybe create a system that switches between using lerp and just hard setting the position of the camera to the intended position based on the angle and the speed of the vehicle, maybe something like that. I'm not sure. I also want to have some control over the pitch of the aircraft. With controller, it makes pretty intuitive sense just to map it to the left stick moving up and down. So if I move the left stick down, the aircraft will pitch up. If I move the left stick up, the aircraft will pitch down, or I guess the spacecraft will pitch down. But how do I do that on keyboard? Because right now, WASD, W and S are being used to accelerate and decelerate the craft. Maybe I can have some sort of like mouse input be linked to it, but that would cause my input system to get a little bit bulkier, which I guess is fine if that's what's required. Maybe I'll play some War Thunder or something and see how they handle it. But yeah, this is what I got so far. Thank you so much for watching the video to the end. Let me know if you have any feedback, any suggestions on how to improve, and I'll see you in the next video.